Hello students, this is Dr. Chakravarti and you are watching our YouTube channel Chemistry for NEET. Today we are going to discuss about resonance. Now what is resonance? Let us explain resonance by some examples. The first question is, why phenol is an acid? Why phenol is an acid? Now what is phenol? Phenol is benzene ring carrying a which group. So if it is an acid, then it must release H plus ion. So if which releases H plus ion, then phenoxide ion is formed, benzene ring carrying a O negative. Okay, so here this H has been released as H plus ion and phenoxide ion is formed. Now let us consider the relative stabilities of phenol and phenoxide ion. Now to consider the stability of phenol, we need to draw all the resonating structures that comes from phenol. Okay, so here oxygen is carrying a lone pair electron. Now that lone pair can get delocalized into the benzene ring through resonance. So how it is possible? Now what is benzene? Benzene is a planar structure. Benzene has a planar structure. Okay, so that is benzene, and each carbon is sp2 hybridized. sp2 hybridized, that means they have made 3 sigma bonds. Each hydrogen has made 3 sigma bonds. Now after formation of this bond, still the pz orbitals remains unhybridized. Now all the pz orbitals are just perpendicular to the bond axis. These are pz orbitals and which are unused. So these pz orbitals being perpendicular with the bond axis and parallel to each other, so they can make a lateral overlapping with each other. They can make a lateral overlapping with each other. Now these two can make a lateral overlapping and these two p orbitals make lateral overlapping. This is how pi bonds are formed. Okay, now if oxygen is there instead of hydrogen, oxygen has also a lone pair and which is also present in p orbitals. So that lone pair, this orbital is also parallel with the pz orbitals of carbon. So here a pi bonding can also be formed. Here a lateral overlapping can also be formed. When it makes the lateral overlapping, these bonds has to be broken and these bonds shifted towards this carbon, okay, as a negative charge. So the bonds are shifting. These pi bonds can be shifted again between these two. Okay, so and this pi bond breaks to form pi bond between these two carbon. That is, here oxygen, the lone pair can be shifted, can make a double bond by overlapping with the pi or pz orbital of carbon. So here a double bond, when a double bond is formed, carbon cannot make more than 4 bonds. So this bond has to be broken and this bonds totally shifted over to this carbon as a negative charge. So this is called resonance. Here we get a canonical structure like here oxygen made a double bond. Since lone pair is given a positive charge, the pi bonds are shifted as negative charge on this carbon and this two pi bonds remain intact. Okay, so this one is the resonating structure, one of the resonating structure of phenol. Now the resonance goes on as this negative charge can also make a double bond between these two carbon atoms. So the number of bonds increases of this carbon, so pi bond shifted over this carbon atom. So we get another resonating structure, double bond OH, here plus, double bond, negative charge. One more resonating structure can also be formed where here double bond, negative charge. So another resonating structure of phenol is this OH plus, negative charge, double bond, double bond. Now when here double bond formed and this bond breaks to oxygen, we again gets this phenol. So these are the 4 resonating structures of phenol, and now we'll draw the resonating structures of phenoxide ion, and then we'll consider the relative stabilities of phenol and phenoxide ion. Okay, so what will be the resonating structures of phenoxide ion? Here phenoxide ion resonance has been initiated by the negative charge on oxygen. Here by this negative charge, oxygen make double bonds here. Now pi bond shifted to this carbon atom, giving rise of a resonating structure, or we can say canonical structure. The negative charge is gone, so oxygen is neutral. Here a negative charge is formed and these 2 bonds remain intact. Now again double bond, negative charge, another resonating structure, double bond, negative charge, then here a double bond and a negative charge, so another resonating structure. So these are the resonating structures of phenoxide ion, and these are the resonating structures of phenol. Now if we consider the relative stabilities of the resonating structures of phenol and phenoxide ion, in all the resonating structures of phenol, a strong electronegative element oxygen is carrying a positive charge. Okay, so if oxygen is carrying the positive charge, this is very much destabilizing factor, because oxygen is electronegative. It always seeking electron from others, and here we can see that oxygen is carrying a positive charge. Due to this, the resonating structures of phenol is very unstable, and again here in the resonating structures of phenoxide ion, no such resonating structure is there here where oxygen is carrying a positive charge. And secondly, in all the resonating structures of phenol, oxygen both positive charge and negative charge coexist. There is also a destabilizing factor for the instability of the resonating structures of phenol due to these 2 factors. Number 1, in all the resonating structures of phenol, a strong electronegative element oxygen is carrying a positive charge, and secondly, in all resonating structures of phenol, both positive charge and negative charge coexist. Due to these 2 factors, phenoxide ion is more stable than phenol. That is why phenol easily dissociates into more stable phenoxide ion, and as a result of that, H plus ion is released. That's why phenol acts as an acid. Okay. Our next question is, between methylamine and aniline, which one is more basic in nature? Between methylamine and aniline, which one is more stable, or sorry, which one is more basic in nature? Now let us consider which one is methylamine and which one is aniline. Now our next question is, between methylamine and aniline, CH3NH2 methylamine, and aniline, that is benzene ring with NH2 group. This one is aromatic amine and that is aliphatic amine. Between methylamine and aniline, which one is more basic? Now first of all, these 2 are nitrogenous base, and their basic strength depends upon their tendency to donate lone pair electrons to others. That means these 2 are actually Lewis base, where lone pair is given by n atom. Now where the availability of lone pair is more, and its tendency to donate this lone pair to others will also be more. Now we have to consider where the availability, that means the electron density on nitrogen is more. Now in methylamine, we know CH3 group has plus psi inductive effect, that means electron repelling effect, so it will repel the bond pair electrons towards this nitrogen, making it's more electron rich. Now when it has greater electron density, it must lose, or it must donate its lone pair electrons more rapidly. That's why methylamine is more basic than aniline. And in aniline, actually, this lone pair of nitrogen is in conjugation with the pi electrons of benzene. That means in alternative positions in pi electrons of benzene. So when it makes a double bond here, that pi electrons is shifted as negative charge on this carbon atom, giving rise of a resonating structure like this. Here double bond is formed, NH2, since nitrogen is given its lone pair electrons, here nitrogen will carry a positive charge, and this pi electrons is broken and a negative charge, here a negative charge is formed, and these two pi bonds remain intact. After then the second resonating, here another resonating structure is formed by negative charge, and this pi bond is shifted to this carbon. Here no pi bond is there, pi bond is forming here a negative charge and a double bond in H2. Nitrogen is carrying a positive charge, the negative charge makes double bond makes negative charge, and this is the basic of resonance. So double bond in H2 plus, negative, double bond. So these are the resonating structures of phenol, and you can see that the lone pair is no longer available on this nitrogen atom, as it is getting delocalized into the benzene ring through resonance. That's why lone pair availability is decreased, and so its donating ability also. So between methylamine and aniline, methylamine is more basic than aniline. This is because methyl group has plus I inductive effect. It repels the bond pair electrons to nitrogen atom, giving or making this nitrogen electron rich, so it can easily donate its lone pair electrons to others. And in case of aniline, the lone pair of nitrogen is in conjugation with the pi electrons of benzene. That's why that lone pair can easily get delocalized into the benzene ring through resonance. Lone pair availability is decreased, and so the basic strength also. Okay, now let us consider another question between phenol and acetic acid. Which one is more acidic in nature? Between phenol and acetic acid, which one is more acidic in nature? Now phenol forms therefore equilibrium in aqueous solution by releasing its hydrogen, acidic hydrogen, and phenoxide is formed, O minus, and acetic acid CH3, C double bond O, single bond OH, by releasing its H plus, it forms the following equilibrium, CH3, C double bond O, single bond O minus. Okay, now let us consider relative stabilities of phenoxide ion and acetate ion. Let us make the resonating structures of canonical forms of phenoxide ion and acetate ion. Now first we consider phenoxide ion. So here O minus, double bond, pi double bond makes negative charge, and so the resonating structures we get is here double bond oxygen, here negative charge, double bond, then negative charge makes double bond makes negative charge. So double bond O, double bond and make negative charge. The negative charge makes double bond makes negative charge. So double bond O and negative charge, double bond. Okay, so these are the resonating structures of phenoxide ion. Now let us consider the resonating structures of acetate ion. C double bond O, single bond O minus. Here negative charge makes double bond makes negative charge. CH3C, O minus, and double bond O, and nothing else. So the number of resonating structures of phenoxide ion is more than that of acetate ion. Here only 2 and here 4, but still acetate ion is more stable than phenoxide ion. This is because these two resonating structures are almost same, not almost, exactly same. They are energetically equivalent, but these are not. Okay, that's why acetic ion is more stable than phenoxide ion. So between these two equilibrium, the equilibrium between acetic acid and acetic ion will lie more towards a forward direction to form more stable acetic ion than phenol. Okay, that's why acetic acid is more acidic than phenol. Okay.